Today we're going to take a look at lesson 5.5, inequalities in two triangles. This goes hand in hand with the last lesson, which was 5.4, inequalities in one triangle. The idea and the concepts that 5.4 introduced is basically just continued in this lesson throughout these examples. So let's go ahead and take a look. So with example 1, investigate side lengths in triangle. Again, remember the stuff that you learned in 5.4, where it was saying that if you have an angle and you're comparing two angles to each other, and the opposite side was shorter with one triangle versus the longer triangle. Hopefully you remember what that kind of talked about and what that introduced in 5.4, because it's kind of just continuing in this lesson. So as a writer pedals a unicycle, how do the measure of angle A and the length of B change? So angle A is the part that's in the middle of the wheel, and then length B is the part between, I guess you'd call it the pedal and the seat. So if you take a look here, here's an example of angle A and then the length of angle B. And then if you look at the next picture, you'll see that angle A increased, it got larger. So maybe the pedal just kept going down. So angle A increased. And then if you look at the length of side B, that also increased. And again, this makes sense, right? This goes back to exactly what we talked about in 5.4. If that angle is small, compared to this angle, right? So angle A right here is smaller than angle A here. Well, that means that this side B, will be shorter than this side B, okay? And then it looks like they go even larger, right? So angle A changes from this part to this part. So it actually gets even bigger, which means that the side gets even longer. So that's all that's trying to say. If two sides of a triangle stay the same, but the measure of the angle between them increases. So one thing you'll notice is that between the seat and the middle of the wheel, that length didn't change, right? That's the same length. Between the middle of the wheel and then the bike pedal, that length didn't change. That's the same length. So the only things that changed were the angle, which then in turn changed that third side length. So we're on page 234. We'll take a look at, they're calling this the hinge theorem. So, think about kind of the example that we just went through and then how that's what this is talking about. So we'll read this narrative real quick. It's probably really confusing, but again, this connects to the idea that we just talked about with the unicycle. If two sides of one triangle are congruent to two sides of another triangle, again, just like that bicycle, right? Between the seat in the middle of the wheel and then between the middle of the wheel and the pedal, those are going to be equal. And the included angles are not congruent, so the angles are not the same, then the longer third side is opposite the larger angle. Again, it's just like that unicycle example we talked about. So that's what that hinge theorem is talking about. Example 2, apply the hinge theorem. So the tension in the exercise band varies proportionally with the stretch distance. So what that's saying is basically the longer you stretch out an exercise band, basically like a rubber band, the longer you stretch it out, the tension is going to increase. So the tension T is described by the function T of x equals K of x. So that's saying the tension of x, right, equals K of x, where K is a constant that depends on the elasticity of the band, and x is the stretch distance. Which position shown in the figures has a greater tension on the band? Well, this kind of goes back to common sense as well. We all know that if we have a rubber band that we only have stretched out that long, right, you can kind of play with it and it's kind of flimsy. But then if you stretch that rubber band out that long, right, the tension gets a lot more, right, it gets a lot more tense. And it's not as flimsy in the middle. Well, the same thing's happening here. Here's the two people they want you to compare. Obviously, the distance, this is important to know, the distance between the arm or the shoulder and the foot is the same with both figures. The distance between the shoulder and the hand is the same with both figures. The only thing that's changing is that the degrees, right? They're starting out at 50 degrees, so it's a little bit off the ground. Now they move up to 80 degrees, so the person raised it further off the ground. And then what that did was it increased the length of the exercise band. So KL increased to KM. When that happens, when this angle increases, well, then what this is saying is the tension of that exercise band is also going to increase. It's going to get tighter, and that makes sense. So this example is basically walking you through that, exactly what that's saying. And it's kind of just getting a little bit confusing. That's why I wanted to explain it before I walked you through all this, the text down here. So the tension of LK is the exercise band. Let me get it down in the picture right here. So the tension of LK is the tension when the angle is 50 degrees. And T of MK is the tension when the angle is 80 degrees, because this is MK right here. Since the measure of MJK, so MJK, that's this angle that's right there, is greater than the measure of angle LJK, so 80 degrees is greater than 50 degrees, apply the hinge theorem. Since MK is greater than LK, the tension of MK divided by that constant is greater than the tension of LK divided by that constant. We don't really care what the constant is. We don't actually have numbers. So they just want to emphasize that when that angle increases, the tension is going to increase as well. Then just like always, right at the top of page 235, we've seen a lot of converse theorems. This is the converse of the hinge theorem. So it's basically saying the opposite. Instead of saying when two sides of one triangle are congruent to two sides of another triangle and the included angles aren't congruent, then the longer side is opposite the larger angle. This is saying the opposite. Now this is saying basically the same stuff, but let me pick it up, and the third sides are not congruent, then the larger included angle is opposite the longer side. It's basically saying the same thing. Just keep in mind that those two things go hand in hand. If you're looking at a triangle and then you're given that third side, the longer third side will be opposite the larger angle, or vice versa. If you're given two triangles with two angles, the larger angle will be opposite the longer third side. So it's kind of saying the same thing, just backwards. Proofs, we're not going to actually prove this theorem. We're not going to walk through it. We're just going to skip proofs altogether. So skip example 3. Example 4, apply the converse of the hinge theorem. So we're basically using the theorem at the top of this page to help us solve this problem. So what are the possible values of x? Well, one thing you'll notice is possible values of x. So we're not actually finding x equals 7 or x equals -3 or whatever, right? They're going to give you a range. What we're going to find is a range of values that could possibly work. So looking at this picture, looks like we've got 3 different triangles here. The first thing I'm noticing is that they're saying that EG, side EG, corresponds to EC because they both have one tick mark, which also corresponds to AC. So all 3 of those sides correspond to each other. They're all congruent. They're all equal. Same thing with EF and DE as well as BC. All 3 of those sides are congruent as well. They're all equal to each other. So just like the theorem states, when 2 out of the 3 sides are equal to each other, to other triangles, you can look at the relationship of those angles. We'll look at this one. For this triangle right here, angle E is 36 degrees, which means that the opposite side, the vertical angle, will also be 36 degrees. They're saying that side GF is 14, side DC is 18, and side AB is 21. So they're giving us a lot of information here. They're only concerned about the side lengths, right? The side lengths right here, that's what we're going to first start looking at. So if you look at these side lengths, you'll notice that this is 14, this is 18, this is 21. So it kind of goes in order, smallest to biggest. So what that tells me is that if this is the smallest side length, or I should say the shortest side length, that means that E, this angle, has to be the smallest angle. If AB, if this is 21, if this is the longest side length out of the three, well, then that means that the side that's, or the angle that's opposite that side, angle C, has to be the largest angle. That's how they work together. So they're saying since FG is less than CD, so FG is less than CD, we know that, and CD is less than AB, apply that converse of the hinge theorem. So here's exactly what they just said. The measure of angle FEG is less than the measure of angle CED, which is less than the measure of angle ACB. I already stated that. If this is the shortest side, that means that that opposite angle has to be the smallest angle. That's why they're saying that FEG is the smallest angle. FEG has to be less than. This is the middle length. So then that means that the side that's opposite that has to be the middle, I guess, value, right? It has to be in the middle of this compound inequality. So that's why CED is there, CED. And because AB was the longest side length, that means that the angle opposite that side has to be the largest angle, which means measure of angle ACB is all the way at the other end. So we know that the measure of angle FEG, we know that it's 36 degrees. So they replaced that with 36 degrees. We know that DEC, or they're calling it CED, is 2x minus 4. So they replaced it with that. And then what is this? ACB is 60 degrees. So they replaced it with that. So at this point, now I have this compound inequality. You'll notice that they're all strictly less thans. So what this is saying is that this side has to be less than this, which has to be less than this. Now I solve. So now I'm just solving for x. If this was 2x minus 4, I'm going to add 4. Keep in mind that if it was 2x minus 4 is less than 60, I would add 4 to both sides. But because we have a 3-part inequality, I need to add 4 to all 3 parts. So 36 plus 4 is 40. 2x minus 4 plus 4 is 2x. 60 plus 4 is 64. Again, if I was given 2x is less than 64, I would just divide both sides by 2 to solve for x. So I have to divide all 3 parts by 2. 40 divided by 2 is 20. 2x divided by 2 is x. 64 divided by 2 is 32. So what that states are the possible values of x for this given problem have to be somewhere between 20 and 32. 20 has to be less than x, which has to be less than 32. Oh, wow, that's it. Page 236, we've got a summary at the top. Again, you just have the 2 theorems, the hinge theorem, then the converse of the hinge theorem. So let's go ahead and jump over to these practice problems and knock these out. So for number 10, we'll call this 10A. Given these 2 triangles, it looks like they're identifying that FE is the same length as SR, KE is the same length as QR. So that's good to know. Now we have that situation like they were explaining with the hinge theorem. What that tells me then is if angle E is 75 and angle R is 60, that means that this angle E, it is larger than angle R, which tells me that the opposite side from angle E, this side, KF, has to be greater than the opposite side from angle R, which is QS, all right? So this angle is larger than this angle, which means that the side opposite that angle has to be longer than the side opposite that angle. So we could set that up. So this is 10A. So that means that 2x plus 3 has to be greater than 15. I solve it just like an equation. If this was 2x plus 3 equals 15, I pretty much do the exact same thing. There is one exception. If we see it, we'll talk about it. Well, I guess I'll throw it out there. If you divide or multiply both sides by a negative with an inequality, then that sign has to flip. So maybe we'll see it, maybe not. We'll see. So if I solve this just like an equation, I get 2x is greater than 12. Divide both sides by 2. I get x is greater than 6. So let's make sure we're answering the question. Write an inequality describing the range of x for each pair. So that's all they're looking for, is just x for that one. 10b. Sorry, that's a rough B. Same kind of situation. Let's see if I can zoom in here a little bit. Looks like, again, AB is congruent with FE, CB is congruent with FD. The angle is 110 over here. The angle is 100 over here. Since angle B is larger than angle F, that means that the side opposite angle B will be longer than the side opposite angle F. So it's going to be 30. So that side is longer or greater than this side. So 30 is greater than 6x minus 12. So now that's a B, by the way. So here we'll solve it. I'll add 12 to both sides. 42 is greater than 6x. Divide both sides by 6. 7 is greater than x. But I like to write it like this. I like to flip-flop, because I always like x on the left-hand side. So if you take that x and that 7 and you flip-flop them, make sure you flip that sign as well. So the greater than becomes a less than. So x has to be less than 7 to make this problem true. 11, write an inequality describing the possible values of x for each pair of the triangles. And you could see examples 3 and 4 if you want to go back and look and see what that's talking about. So with this one, they're giving you that JL is the same length as MP. They're giving you that JK is the same length as MN. They're giving you that angle J is 75, angle M is 4x minus 25, and then they're giving you those side lengths as well. So with problem 11a, it's kind of more the same. They're telling you that this side length is 39, this side length is 32, which means that LK is longer than PN. Since that's the case, since this side is longer, that means that this angle has to be greater than this angle over here. So it's basically the opposite of problem 10. Instead of going off of the angles, now we're going off the side lengths. So I'm going to pick the longer of the two sides, which is 39 right here. And I'm going to say that 75 degrees, so 11a, 75 degrees has to be greater than, again, because that's the opposite of the longer side, has to be greater than angle M, 4x minus 25. And now, just like before, solve. So I'll add 25 to both sides. I get 100 is greater than 4x. Divide both sides by 4. I get 25 is greater than x. I don't like to leave it like that. I always like my variable on the left. So I'm going to flip-flop those two, x and 25. Just make sure you flip-flop that sign. So x has to be less than 25. B is exactly the same. So it looks like with this triangle, this side is actually shorter than this side. So that means since this side is shorter, the angle opposite of that side has to be smaller than this angle over here. So I'm going to say 3x plus 17. 3x plus 17 has to be less than 77. Let me just make sure I looked at the right one. Yep. Now I solve. Subtract 17 from both sides. 3x is less than 60. Divide both sides by 3. X is less than 20. 12, write an inequality describing the possible values of x for each diagram. So this relates back to, I think it was example 4 that we looked at when we're setting this up. So with this example, they're giving us a lot of information. They're giving us that GH, it's not necessarily equal or congruent with any other side. GK is 29, JK is 29, HJ is 25, and then they're giving us those two angles in the middle there. So this one's a little bit tricky. I hate using the word tricky because I don't want you to think they're trying to trick you. They're just trying to test you to make sure that you know what you're looking for and you can derive the correct information. So I said at the beginning that this side is not congruent with this side, but what do you notice about the third side of the triangle that we never talked about, right? Those two triangles are sharing that side. So that means that JK is going to correspond. It's got to be congruent with I'm sorry, I think I said JK. GK is congruent to JK, and that HK for this top triangle has to be congruent to HK for the bottom triangle because it's literally the same side, okay? So what this is telling me is that this side is 21, this side is 25, so that means this side is shorter, so that means that the angle opposite that side has to be smaller than the angle opposite this side. So 40 degrees, this is 12A, 40 has to be smaller, less than 3x plus 4. So not too bad, just kind of keep those two main ideas in your head. If you're looking at two side lengths, the longer side will always be opposite the larger angle and vice versa. If you're looking at two angles, the larger angle will always be opposite the longer side. So it's basically the same thing. So we'll subtract 4 from both sides. 36 is less than 3x. Divide both sides by 3, and I get 12 is less than x. But again, I'm going to flip-flop it. X is greater than 12. We got 12b, pretty much the same thing. Let's just check it out and see if they're doing the same thing to us. AB is 25, BC is 25, CD is 39, AD is 2x plus 17, and then they're giving us those two angles there. So this is basically doing the opposite of what this is doing. Okay, this is the converse of it. So they're telling us that these two angles, when you're looking at them, angle B down here, that's 133. That's definitely larger than the angle B up here. So that's telling me, since this is the larger angle, that CD, this side, has to be the longer side. So 39 has to be greater than, this smaller angle. So the opposite of this is the shorter side, 2x plus 17. 2x plus 17. Now we have an inequality. Go ahead and solve it. Subtract 17 from both sides. That's 22 is greater than 2x. Divide both sides by 2, and I get 11 is greater than x, or x is less than 11. So as you're going through this and taking a look at it, if you want to talk about it some more, just shoot me an email or stay after class, and I'm happy to do that.